Good day everyone. So for today, I'm going to start with phase equilibria, a fundamental principle in the understanding of separation processes. Now it has two words, phase and equilibria. So when we speak of phases, it has something to do with liquid, solid, or gas phases. And when we speak of equilibria, it came from the word equilibrium. Now, the degree of separation or the extent of recovery of a particular component from a mixture is dictated by this concept of what we call equilibrium. Now, let us remember that mass transfer ceases when an equilibrium between the two phases that were contacted is reached. So even if we lengthen the amount of time in which these two phases are intimately contacting each other, mass transfer already ceases when equilibrium is reached. Now the rate of mass transfer in here is directly proportional to the driving force, and this driving force is a departure from what we call equilibrium condition. So the rate, take note, the rate of mass transfer is directly proportional to the driving force. Now to be able to evaluate the rate of mass transfer, the driving force has to be accurately determined, which in turns rely on the equilibria between phases. Now in nearly all situations, two phases are involved, except in the case where we are contacting two solid phases. Now, in the usual case, and in almost all separation processes, the controlling variables are the intensive properties, temperature, pressure, and concentration. They are intensive in the sense that they are not whatsoever affected by the amount of material that are being contacted. Now, when we present equilibrium data, or when we want equilibrium data to be taken from other sources or from several sources, you have these three that are available. So whichever of the three is applicable for a particular problem that you are solving, or for a particular situation in which you are in need of an equilibrium data, then you might use any of this. Now, when you speak of tables, just like this one, this is an example of a table which contains the equilibrium data for a system which is so common, an ideal system of benzene and toluene. Now in the first two columns here, you have the temperature. The next two columns would be that for benzene vapor pressure, and the next two columns again will be that for the vapor pressure of toluene, and the last two columns will be for the mole fraction of benzene. This is for the liquid phase, for the XA, and for the YA, that would be for the gas phase. Now, when we speak of the system benzene and toluene, A refers to benzene. Now, how do we interpret the data that we are seeing in this table? In problems, we are usually at all times given the temperature. So given the temperature, you will be able to pick from a column, from a specified column, depending on the unit that you want to use for vapor pressure, the values of vapor pressure of benzene and toluene. So let's say I want the vapor pressure of benzene and toluene at 110.6 degrees Celsius. Then I will just simply read to a particular column, or from a particular column, a value that I need with the same unit as indicated in the problem. But if the problem does not indicate any of the units for pressure, then you may choose from any of the two columns that we have in here. Again, we base the vapor pressure from the temperature in the first two columns. Now, the last two columns can also be sought after when we want to know what is the mole fraction of benzene in the liquid phase, and that is XA, and what is the mole fraction of benzene in the gas phase, again given the temperature. So this is just one form in which we can extract equilibrium data, provided that we are given the temperature. Now, this graph is linear graph. But let's say, for example, you are given a temperature that is not written in this graph. You can approximate by using interpolation or extrapolation, whichever may apply. But in reality, if you want something that is accurate, you are not supposed to interpolate or extrapolate from the given data here, because the behavior of our system is not linear. So it's not linear, meaning it does not behave using the approximation of Henry's law, which we will be discussing in a little while. But in the absence of any data that you can use, then you will approximate, or you may approximate by interpolating the temperature that is given in the problem based on what is provided here. Now, let's continue. So this is just but one of the ways in which equilibrium data is presented. Now, equilibrium data can also be presented in the form of equations, or it could be, shall I say, calculated from a given equation. So what are these equations? So the common equation that we use to express relationships of, let's say, partial pressure with mole fraction of A in the liquid phase is Rayols Law. So in here, you're given a linear relationship between partial pressure of A in the gas phase in terms of its mole fraction in the liquid phase. This capital P sub A is the pure vapor pressure of A. Where do we get this? We get this from property tables or from appendices in our respective major reference materials, or in any book that has this particular data. So the relationship is linear. Now, there's a note here that Rayols law is only applicable for ideal solutions. And when do we know that solutions are said to be ideal? So we say a solution is ideal if the behavior of the components or their characteristics are more or less the same. If the problem does not specify it, we are not to assume that our system is ideal. So there has to be an alternative formula that could be used, an alternative equation to be used, if we're not allowed to assume if a system is not specified to be ideal in the problem. And that is the Henry's law. So Henry's law does not have any limitation. It can be used for ideal system as well as for non-ideal systems. In here, you're still determining the partial pressure of a gas, let's say A, and it is also linear with its mole fraction in the liquid phase. However, you have now the appearance here of Henry's constant, or specifically we refer to this as the Henry's law constant. Now, this particular constant can be taken again from appendices in your textbooks or from our chemical engineer's handbook. Specifically in section 2, if you cannot find it in section 2, go to the section that discusses vapor-liquid equilibria. Now, if the equation that we have here is divided by the total pressure of the system, the resulting equation would look something like this. The partial pressure divided by the total pressure of our system will now represent the mole fraction of A in the gas phase. And the H, the original H, is converted to H prime. And as you could see here, it's now equal to the original H divided by the total pressure P. In the original equation, the only identity that was preserved is the XA. It was preserved because in the new equation, after division by the total pressure P, XA is still XA. So again, Henry's law does not have any limitation. Now, in liquid extraction, you may encounter, or we will be discussing, the K-factor distribution coefficient. This can also be used in the case of determining the relationship between mole fractions of a particular component I in the gas phase and in the liquid phase at equilibrium. And as such, you see the subscript here, IE. I represents a particular component and E is representing equilibrium condition. Now, this could also be replaced by an equivalent equation giving you the same exact answer here if Rayols law and Dalton's law hold. So meaning, this could be replaced by this particular formula if your system is ideal and if the law of partial pressures of Dalton will be applicable. You can replace this y and x here by the partial pressure of the component I divided by, or rather by the pure vapor pressure of component I divided by the total pressure of the system. So again, the P sub I prime is the pure vapor pressure of I. But this again is only applicable in this scenario. Now, if Rayols law holds, then the ratio of the K factors and relative volatility of the components are the same. So what does that mean? If we want to get the ratio of the two distribution coefficients of the components I and J of your mixture, if Rayols law apply, that would be also the same as this one. You eliminate the total pressures in the previous formula in here, because anywhere you were talking about ratio and they will cancel each other in here. So you have simply this one. So the relative volatility of component I with respect to J is just equal to the ratio of their K factor distribution coefficients. We will go back to this when we will be discussing already liquid-liquid extraction. Now, K factors are to be remembered as strongly temperature dependent. So, meaning as the temperature changes, its value also changes. But for relative values of K, for two components, the change is only moderate. It does changes, but the change is moderate. So, in terms of equations that are available that expresses relationships of pressures, mole fractions, relative volatilities in a particular mixture, we have three so far. Rayols law for ideal solution, Henry's law, and the K factor distribution coefficients. Now, another way of presenting equilibrium data is in the form of graphs. So we have discussed the tables, the equations, and now we go to graphs. Now, graphs can be in this form, and you can see an exact equivalent of this in your textbooks. Now, some graphs may express mole fractions against partial pressure, and that's in the case of Henry's law. It approximates the nonlinear behavior of mole fraction of A versus its partial pressure, which is in here is actually curved. The behavior is curved, but Henry's law linearizes it. So this one also, this particular diagram can also give you the relationship of XA and P sub A. Now, another diagram would be relationship between XA and YA. This one is XA and P sub A. This one is XA and YA. So you get the X's here, you go up, and then read on the curve the corresponding mole fraction in the vapor phase. So let's say, for example, you have a 0.6 mole fraction of A in the liquid phase. You go up until you reach the curve, and then you read here on the left side its corresponding YA. If you're using this graph, that would be the same. Given XA, you go up, you use the linearized line or the line for Henry's law. If you don't want to approximate, you can use the curve in here on top of this line, and then stop where you already reached the curve or the line, and then project on the left and read the corresponding partial pressure. So knowing one will help you know the other. So XA will give you YA for this. XA here will give you P sub A for this. This curve giving you XA and YA, or it could either be XA or YA on the x-axis, and on the vertical axis you have temperatures. Well, what's the purpose of this boiling point diagram? And this is only for benzene and toluene. So meaning if we have a different system, we will have a different diagram as well. The curve has, this particular diagram has two curves. This one is the liquid saturation curve, and this one is the saturated vapor curve. If we are given the mole fraction in the liquid phase of a particular component in the mixture, if you want to know when will it boil, you have to go up straight until you reach the saturated liquid line or curve, and then read out the corresponding temperature here. Again, what is this temperature? This is the temperature in which this particular concentration of A in the liquid phase is going to boil. So you end up here on the bubble point liquid line or the saturated liquid curve. Now, if you would be asked when will be or what is the condensation temperature of your gas, what do you need to do? Given the YA, from here, because this particular axis is both for XA and YA, you go up until you reach the second curve. And this is the dew point vapor line or the saturated vapor curve. You read on the side the corresponding temperature in which it will start to condense. What happens if you have a point somewhere in between these two curves? And you would be asked what would be the state of this particular mixture in this particular point here. At this particular point, we are saying that you have already a mixture of liquid and vapor, because this one is the vapor liquid mixture region. Now, again, you may wonder, what is this line? Why is it that from B I go left rightwards until here? It will answer the question, what would be the composition of the vapor in equilibrium with this liquid at this particular concentration. For example, you have the composition of 0.4 of A in the liquid phase. Now, you would be asked, what is its boiling point? You go up, you stop here, and then you read on the left side the boiling point temperature of this particular mixture, which has 0.4 as the concentration of A, whatever that A may be, or in this case that would be benzene. Now, if you would be asked what is the corresponding composition of your vapor in terms of A when its liquid composition is 0.4, you go rightwards until you reach this point here, and then go down, and then go down and read the YA here on the x-axis. So now, given one, you get to get two information: the boiling temperature of your mixture and the composition of the vapor in equilibrium with this particular liquid having this concentration. So this particular data we get from the boiling point diagram of a particular system. Whereas the one that we have on the left side have only two informations available for us to use. This one may have 2 and even 3. Okay, so that is the use of the diagram in terms of getting equilibrium data of. Now, for most operations, however, the pertinent equilibrium relationships are shown graphically. So, meaning of these three, tables, equation, and graphs, majority are being taken from graphs. And then from the graphs, we may use it together with the equation to solve the other information that the problem may require from us. So that is the case of the phase equilibria. Now, what are the bases for phase equilibrium? So we have the phase rule. So in the phase rule, we have F as the degrees of freedom or the variance. The C would be the number of components of your particular mixture, and the P, the number of phases that are being contacted. And this is the general formula in determining the phase rule. Now, we are defining here the degrees of freedom. So, the number of independent intensive variables, examples of which are temperature, pressure, and concentration, that must be fixed to define the equilibrium state of the system. So, meaning, I need to fix 2. If my answer in the previous equation is 2, I need to fix 2. That way, I can find whatever is the problem is asking from me, as long as the informations provided are valid. Because it says it's the number of independent intensive variables that should be set or should be defined so that we will know what would be the equilibrium state of our system. What will happen if there are fewer than the F variables that were given in the problem? So if fewer than F variables are fixed, an infinite number of states fits the assumption. So meaning, it's impossible to compute or to calculate for what the problem requires. While if F is more than what we have computed, or the number of variants that we computed from the formula is higher, or the data is higher than the computed F rather, the system is said to be over-specified. Just like the concept in algebra of number of unknowns should be equal to number of equations, so that we will have an answer to the given set of equations. So if we have less number of equations than unknowns, impossible to solve the problem. If we have more than, then we have what we call an over-specified set of equation. So meaning we can have a lot of answers for that. Now for an example, for a two-phase system, variance is equal to 2, which also is equal to the number of components of that particular two-phase system. In our case, it would be always like this. We limit our system to be a two-phase system having 2 components. If, for example, we fix pressure, the liquid phase concentration can be changed independently. Then the gas phase composition and temperature for a liquid gas equilibria can be determined. So we have, let's say for example, pressure is given, the liquid phase composition can be given, but it is independent of this pressure. With these two, then it says here, we can determine the composition and the temperature of the gas phase. We are given the pressure and the liquid phase concentration, which is independent of the pressure, because we have 2 as our variance. Then if we would be asked by the gas phase composition and temperature, we can do that because the number of independent variables that were provided is equal to 2, and that is pressure and the liquid phase concentration. Now moving on, let's say we'll have some sample problems illustrating the use of the formulas discussed and the use of the table and the diagram. Now, in sample problem number 1, it says that the partial pressure of carbon dioxide in air is 1.333 times 10 raised to 4 Pascal, and the total pressure is 1.1333 times 10 to the 5th Pascal. The gas phase is said to be in equilibrium with the water solution at 303 Kelvin. What is the value of XA? That is the composition of CO2 in the liquid phase that is said to be in equilibrium in the solution. Now, the Henry's law constant for CO2 can be taken from Perry's handbook or from appendices that you have in your textbook, at the back part of your textbook and major reference books. In the case of John Copley's, at the designated temperature, you have this value for Henry's constant. Now, Henry's constant has a set units equal to atm per mole fraction. So, if you recall our discussion a while ago, we have Henry's equation being partial pressure of A equal to Henry's constant times the mole fraction of A in the liquid phase. Now, we have to be very careful as to these types of problems because they look very easy. Actually, it's just substitution to the formula. However, you have to make your units agree. If you place here a partial pressure of 1.333 times 10 to the 4th Pascal for that of the partial pressure of CO2, its unit is Pascal. However, the data for Henry's law constant is in atm. So, there's a need for you to convert from Pascal to atm. And this is the conversion. Now, we place on the right side of the equation Henry's law constant, the one that is given here. And then, we already have the corresponding unknown in the problem. And that is the mole fraction of CO2 in the liquid phase. By the way, whenever you see a subscript in a particular X or Y, that refers to that particular component that is stipulated in the problem. And whenever you see a G on our slides, that means that the problem is based upon John Copley's. Now, if we look at another problem, we're given, again, CO2 at a temperature of 303.2 Kelvin. This CO2 is with water in a CO2 water system. Their mass ratio, so I say mass ratio, it's because the unit here are in kilogram CO2 per kilogram water. And their mass ratio is 0.9 times 10 raised to negative 4. Now, we are to use Henry's law constant, and these are the required informations. What partial pressure of CO2 must be kept in the gas to keep the CO2 from vaporizing from the aqueous solution? So, it's asking for the partial pressure of CO2 in the gas so that it will not vaporize from the aqueous solution. So, meaning to keep the CO2 dissolved in the CO2 water solution, what should be the partial pressure of CO2 above this CO2 water mixture? This is in the case of CO2 dissolved in water. Now, the first thing that you are to do is convert the mass ratio that you are provided here for CO2 and water to mole ratio. Wonder why? It's because we cannot use mass ratio in problems concerning equilibrium because we're dealing with molar concentrations. So, in doing that, we need the atomic weights, or rather, not the atomic weights, but the formula weights of CO2 or molecular weights of CO2 and water. And we make use of that to convert the mass ratio to mole ratio. And we have it here. After you have done converting mass ratio to mole ratio, you determine the total number of moles of your mixture. From your answer here on the mole ratio, it says that you have 3.682 times 10 raised to negative 5 mole CO2 for every mole of water. So, meaning the total number of moles of your mixture would be now the sum of this 3.682 times 10 raised to negative 5 and 1 mole water. And that would be this one. Why get the total number of moles? You want to determine the mole fraction of CO2 now in your liquid. So, you have the moles of CO2 divided by the total number of moles, and this would be your answer. Why do you need to get this? Because you need the XA in determining the partial pressure of CO2 above the mixture using Henry's formula. So, all the rest here is substitution because you have placed in here 0.168, and then you have atm per mole fraction, and this one And this would be the corresponding partial pressure above the mixture to keep CO2 from vaporizing.